All right, let's go. For most of human history, the night sky was the boundary of the unknown. Then we built telescopes, and the boundary moved. We discovered galaxies, nebula, the cosmic microwave background, the large-scale structure of the universe. With every new instrument, with every new generation of scientists, we pushed the frontier further back. We felt, somewhere deep in the collective confidence of modern physics, that we were closing in, that the universe was becoming legible, that we were learning to read it. Then we looked at black holes, and the universe stopped making sense. A black hole is not merely a very dense object. It is a place where the laws of physics as we understand them collapse entirely, where the two greatest intellectual achievements in human history, Einstein's general relativity and quantum mechanics, are forced into direct contact with each other and immediately begin producing results that are mathematically incoherent, where space and time themselves stop behaving like space and time, where concepts like direction, temperature, information, and even causality, the idea that causes precede effects, begin to break down. What follows is not a list of curious footnotes. These are 10 anomalies, 10 places where scientists built models, ran experiments, made predictions, watched the data come in, and were forced to stand in front of the evidence and say, we were wrong. Not slightly wrong, not approximately wrong, fundamentally, structurally, deeply wrong, in ways that reach all the way down to the foundation of what we thought we knew about reality. This is where physics goes to break. Let us begin. Number 1. The singularity. Physics produces an infinite answer and calls it an answer. When Einstein published his field equations of general relativity in 1915, he was uncomfortable with what they implied at their extremes. The equations described how mass curves spacetime, how gravity bends the fabric of the cosmos. They were, and remain, the most precisely verified equations in the history of physics. GPS satellites require corrections based on general relativity to stay accurate. Gravitational waves, detected for the first time in 2015, matched Einstein's predictions exactly. The equations work, except for one thing. At the center of a black hole, the equations produce a singularity, a point of infinite density, infinite temperature, infinite spacetime curvature. And in mathematics and physics, when your equation outputs infinity, it does not mean the answer is very large. It means your equation has broken. It means your model has hit its own boundary and can no longer describe what is actually happening. Physicists knew this almost immediately. Roger Penrose proved in 1965 that singularities are not a quirk of simplified mathematical models. They are a generic, inescapable prediction of general relativity. Any region of space that collapses sufficiently will produce one. Penrose won the Nobel Prize for this work in 2020. The problem is that nobody believes singularities actually exist. A genuine physical infinity, an actual point in space where density is literally, not metaphorically, infinite, is not a thing the universe contains. It is a thing that equations contain when they stop working. Stephen Hawking himself, whose name is attached to some of the most important work ever done on black holes, spent the last decade of his life trying to reformulate the theory to eliminate the singularity. He did not succeed. What sits at the center of a black hole, in reality, is unknown. We have a mathematical placeholder, the singularity, that tells us our best theory of gravity cannot describe it. What replaces it, what the actual physics of that region is, whether space and time continue to exist there in any recognizable form, is something we cannot currently answer. The most honest thing physics can say about the center of a black hole is, we have no idea. And that fact alone, that the universe contains regions that our best equations cannot describe, is the original, foundational anomaly from which everything else on this list descends. Number 2, the information paradox. Hawking spent 40 years being wrong. In 1974, Stephen Hawking made a discovery that he himself described as one of the most surprising results of his career. By combining quantum mechanics with general relativity, an uncomfortable marriage at the best of times, he calculated that black holes are not perfectly black. They radiate. Slowly, imperceptibly slowly, but continuously. Due to quantum effects at the event horizon, black holes emit thermal radiation and gradually lose mass. Given enough time, far longer than the current age of the universe, a black hole will completely evaporate, popping out of existence with a final burst of radiation. This discovery was celebrated as one of the great theoretical achievements of the 20th century. It was also, almost immediately, recognized as a catastrophe. Here is the problem. The radiation Hawking calculated is thermal. It is random. It carries no information about what fell into the black hole to create it. A black hole that formed from a collapsing star and a black hole that formed from a collapsing library of books would, according to Hawking's calculation, produce exactly identical radiation. Every detail about what went in, every atom, every quantum state, every bit of information would be permanently, irretrievably destroyed. But quantum mechanics has a fundamental rule. Information cannot be destroyed. It is not a preference. It is not a convention. It is a mathematical theorem baked into the foundations of quantum theory. If information were truly destroyed in black holes, the entire mathematical structure of quantum mechanics would collapse. The equation that describes how quantum systems evolve over time, the Schrödinger equation, would be violated at a fundamental level. For 40 years, this was the information paradox. Hawking argued on one side. Physicists like Leonard Susskind and Gerard 't Hooft, both Nobel laureates, argued on the other. The debate was so fierce, so prolonged, and so foundational that Susskind wrote an entire book about it called The Black Hole War. In 2004, Hawking conceded publicly. He announced at a conference in Dublin that he had been wrong, that information is not destroyed, that it must escape somehow, encoded in subtle correlations in the Hawking radiation. He did not explain how. Nobody has fully explained how. The mechanism by which information escapes a black hole without violating either general relativity or quantum mechanics remains one of the most actively debated problems in theoretical physics. Hawking changed his position. The paradox remained. Number 3. The firewall paradox. The solution was worse than the problem. By 2012, a partial consensus had emerged around how information might escape a black hole. The idea was called black hole complementarity, developed largely by Susskind. It proposed that information was somehow encoded in the Hawking radiation through quantum entanglement between particles inside and outside the event horizon. It was mathematically subtle, it was deeply counterintuitive, but it seemed to hold together. Then, 4 physicists, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully, published a paper that destroyed it entirely. The paper became known as AMPS, after their initials. Their argument was simple and devastating. If information is truly encoded in correlations in the Hawking radiation, then the radiation particles outside the black hole are maximally entangled with the radiation particles emitted earlier. Quantum mechanics has a law called monogamy of entanglement. A particle can only be maximally entangled with one other system at a time. But for general relativity to work smoothly at the event horizon, for an astronaut falling in to notice nothing unusual at the moment of crossing, the particles outside must also be entangled with particles inside. Both things cannot be true simultaneously. Something has to break. The AMPS paper argued that what breaks is the event horizon itself, that the gentle, smooth boundary described by general relativity is, in reality, a wall of infinite radiation, a firewall. Anything attempting to cross the event horizon would be instantly incinerated, not compressed, not stretched, not gradually destroyed, incinerated at the boundary. This violated everything we thought we knew about event horizons. It violated the equivalence principle, one of the foundational postulates of general relativity. It meant that Einstein was wrong, not in the extreme conditions of the singularity, but at the event horizon itself, in a region where space-time curvature is actually quite modest for large black holes, and where, under general relativity, physics should look almost normal. The firewall paradox has not been resolved. String theorists, loop quantum gravity researchers, and information theorists have all proposed responses. None has achieved consensus. What the AMPS paper demonstrated was not just that one theory was wrong. It demonstrated that the 3 pillars of the problem, general relativity, quantum mechanics, and information theory, cannot all simultaneously be correct. At least one of them is failing us at the event horizon of every black hole in the universe. We do not know which one. Number 4. Spaghettification is not what we thought. Time destroys you before gravity does. The popular image of falling into a black hole involves tidal forces. The gravity at your feet is stronger than the gravity at your head. You get stretched into a long, thin strand of matter, like pasta. This process has the scientific name spaghettification, and it is real. For stellar mass black holes, those a few times the mass of the Sun, the tidal forces at the event horizon are so extreme that a human body would be pulled apart long before reaching the boundary itself. But for supermassive black holes, the kind that sit at the centers of galaxies, containing millions or billions of solar masses, the situation is different. The event horizon of a sufficiently large black hole is so far from the singularity that the tidal forces at the horizon are actually quite gentle. A human body crossing the event horizon of the black hole at the center of the Milky Way, Sagittarius A star, which contains 4 million solar masses, would not be spaghettified. Not immediately, not at the boundary. What actually kills you before tidal forces become significant is time. As you approach the event horizon, according to general relativity, time dilation becomes extreme. The gravitational time dilation near a black hole is not a small correction. It is total. At the event horizon itself, from the perspective of a distant observer, time stops entirely. A clock falling toward the event horizon would appear, from far away, to slow down asymptotically, its rate approaching zero, but never actually reaching zero, its final tick stretched across an infinite span of time. From your own perspective falling in, you cross the event horizon in finite, ordinary-feeling time. But inside the event horizon, the radial direction, the direction pointing toward the singularity, ceases to be a direction in space. It becomes a direction in time. The singularity is not a place. It is a moment, a future moment that every particle inside the event horizon is inevitably approaching, just as surely as every particle outside the event horizon is inevitably approaching its own future. There is no direction you can accelerate in to avoid it, because you cannot accelerate away from the future. Inside a black hole, your destruction is not a location. It is your destiny in time. Number 5. Black holes have temperature, and that should be impossible. Temperature in physics is a measure of the average kinetic energy of particles. Hot objects radiate energy. Cold objects absorb it. A perfectly black object, one that absorbs all incoming radiation and reflects nothing, would be in thermal equilibrium at the temperature of its surroundings. In the vacuum of deep space, far from any star, that temperature approaches absolute zero. About 2.7 Kelvin, the temperature of the cosmic microwave background. Black holes absorb everything. Nothing escapes. Therefore, black holes are perfectly black. Therefore, black holes should be at or below the temperature of the cosmic microwave background. This was the consensus before 1974. Then, Hawking showed that black holes have temperature. Specifically, a black hole's temperature is inversely proportional to its mass. The smaller the black hole, the hotter it is. A stellar mass black hole has a temperature of approximately 60 billionths of a Kelvin, far colder than the cosmic microwave background, and therefore net absorbing radiation from its surroundings, not emitting. But a black hole the mass of a mountain, if such a thing exists, would have a temperature of billions of Kelvin. It would be blazing hot, radiating energy furiously, shrinking rapidly, and ending its life in an explosion comparable to millions of nuclear weapons. The fact that black holes have temperature is deeply strange. Temperature implies thermal equilibrium. Thermal equilibrium implies information can leak through. But nothing can leak through an event horizon. Jacob Bekenstein had proposed, before Hawking's calculation, that black holes have entropy, a measure of the amount of information hidden inside them. He faced enormous resistance. Physicists felt that assigning entropy to a black hole was a category error. The resistance evaporated when Hawking independently derived the temperature. If a black hole has temperature, it must have entropy. Bekenstein was right. And the amount of entropy a black hole contains, encoded not in its volume, but in the area of its event horizon, is greater than any other object of the same size in the universe. A black hole is the most efficient information storage device that physics permits. We do not know why. We do not know what stores that information. We know only that it is there. Number 6. The holographic principle. Reality might be two-dimensional. The entropy of a black hole led to one of the most radical proposals in the history of theoretical physics, one that began as a mathematical conjecture and has since accumulated enough supporting evidence that some of the most respected physicists alive believe it may be literally true. The entropy of a black hole scales with the area of its event horizon, not its volume. This is bizarre. For any ordinary physical system, information content scales with volume. A hard drive twice as large stores twice as much data. A box of gas twice the volume contains twice as many molecules with twice as many quantum states. Volume scales with information, always, except in black holes. Gerard 't Hooft and Leonard Susskind realized that this was not just a quirk of black hole thermodynamics. It was a deep hint about the nature of reality itself. If the maximum information content of a region of space is determined by its surface area and not its volume, then perhaps the three-dimensional interior is, in some deep sense, encoded on the two-dimensional boundary. Perhaps the bulk of space, the three-dimensional world we experience, is a kind of projection from a lower-dimensional surface. This is the holographic principle, and in 1997, physicist Juan Maldacena provided it with a concrete mathematical realization. He showed that a specific theory of gravity in a three-dimensional space is exactly mathematically equivalent to a quantum field theory living on the two-dimensional boundary of that space. The two descriptions, one with gravity, one without, describe exactly the same physics. Neither is more fundamental than the other. The implication, if Maldacena's correspondence generalizes, is that our three-dimensional universe, complete with gravity, with mass, with all the complexity of space-time curvature, may be entirely equivalent to a two-dimensional quantum system with no gravity at all. That the depth we perceive, the third dimension of space, the apparent solidity of the world, may be emergent, not fundamental, a hologram in the most technically precise sense of the word. Scientists have not admitted this is certainly true. They have admitted that they cannot find anything wrong with the mathematics, and after 25 years of trying, that amounts to a very unsettling kind of endorsement. Number 7. Hawking radiation has never been detected. And the reason why is its own problem. Everything we have discussed about Hawking radiation, the temperature of black holes, the information paradox, the firewall, the slow evaporation over cosmic timescales, is based on a theoretical prediction, a calculation, a result produced by combining quantum field theory with the curved spacetime of general relativity. We have never detected Hawking radiation, not once, not a single photon. This is not because we have not tried. It is because for any black hole we know exists, from the stellar mass black holes formed by collapsing stars to the supermassive black holes at galactic centers, the predicted Hawking temperature is so extraordinarily low that it is completely drowned out by the ambient radiation of the universe. The cosmic microwave background radiates at 2.7 Kelvin. Stellar mass black holes radiate at roughly 60 billionths of a Kelvin. The signal is more than 10 orders of magnitude below the noise floor of the universe itself. The only black holes that would radiate detectably are primordial black holes, hypothetical objects formed in the extreme density of the early universe, small enough to have evaporated or be near evaporation today. If a primordial black hole of the right mass exists near enough to us, its final evaporation would produce a detectable gamma-ray burst of a very specific character. We have searched for this signature. We have not found it. We cannot distinguish between the possibilities. The most important theoretical result in the history of black hole physics, the cornerstone upon which the information paradox, the firewall paradox, black hole thermodynamics, and the holographic principle all rest, has zero direct experimental confirmation. Physicists proceed with enormous confidence in a result they cannot test. And the reason they cannot test it is itself a consequence of how extreme black holes are. The universe has placed its most fundamental secrets inside objects so extreme that our instruments cannot see into them, and the radiation they emit is too cold for the universe itself to be quiet enough to detect. Number 8. Time stops at the horizon, but Hawking radiation requires time to flow. This is the paradox that causes genuine headaches at physics conferences. It involves holding two things in mind simultaneously, both of which appear to be true, and watching them contradict each other in slow motion. From the perspective of a distant observer watching an object fall into a black hole, time at the event horizon slows to zero. The infalling object asymptotically approaches the horizon, its image redshifting to invisibility, its clock appearing to stop. From this perspective, nothing ever crosses the horizon. The surface of the black hole is a frozen record of everything that has ever fallen toward it, time dilated to a standstill. Hawking radiation is emitted from the event horizon. It requires quantum processes to occur at the event horizon. Quantum processes require time to pass. If time stops at the event horizon for a distant observer, how does the event horizon manage to emit radiation through a process that requires time? The answer involves the distinction between coordinate time, the time measured by a distant observer, and the proper time experienced by a local observer. In the quantum field theory calculation Hawking performed, the radiation arises from the vacuum structure of spacetime in the curved geometry near the horizon. It does not require a classical process happening at a specific moment in coordinate time. It arises from the global structure of the space-time geometry. But this answer, while technically correct in the framework where Hawking derived his result, becomes deeply unclear when you try to ask what is actually happening, physically, at the horizon. The two descriptions, the distant observer's frozen horizon and the quantum mechanical radiating boundary, are produced by different theoretical frameworks that were not designed to talk to each other. When you try to make them talk, they argue. The event horizon is simultaneously frozen and radiating, depending on which framework you use to describe it. And we do not have a framework that is valid for both. Number 9. Black holes merge in ways that violate classical expectations. And LIGO proved it. On September 14, 2015, the LIGO gravitational wave detectors registered a signal. It lasted less than a second. It was a chirp, a rising frequency that peaked and then cut off. The data, when analyzed, showed that two black holes, one of approximately 36 solar masses and one of approximately 29 solar masses, had spiraled together and merged into a single black hole of approximately 62 solar masses. 3 solar masses of pure energy have been radiated away as gravitational waves in that fraction of a second. More power, for that instant, than all the stars in the observable universe combined were emitting as light. This confirmed gravitational waves. It confirmed the existence of binary black hole systems. It won the Nobel Prize in 2017. It was one of the great observational triumphs of modern science. It also revealed something unexpected. Black holes were found in mass ranges, particularly between about 55 and 130 solar masses, where they were not supposed to exist. Stars in this mass range are predicted by stellar physics to undergo pair instability supernovae, explosions so complete that they leave no remnant behind. No neutron star, no black hole, nothing. The mass gap was supposed to be empty. LIGO found black holes there. Either stellar physics is wrong, or these black holes formed through a different mechanism, perhaps hierarchical mergers, where black holes merge in dense clusters to build up mass step by step. Or something else is happening that we have not identified. The universe is producing black holes in the places physics said were forbidden. And with each new gravitational wave detection, the confidence in our models of black hole formation erodes a little further. Number 10. The black hole at the center of our galaxy behaves in ways that have no explanation. Sagittarius A star is 4 million times the mass of the Sun. It sits 26,000 light-years from Earth at the center of the Milky Way. In 2022, the Event Horizon Telescope collaboration released the first direct image of it, a blurry ring of light around a central dark region, exactly as general relativity predicts an event horizon should look when surrounded by heated, infalling matter. The image was a triumph. It was also immediately surrounded by questions. The plasma environment around Sagittarius A star is violently, chaotically variable. It flares on timescales of minutes to hours, extraordinarily rapid for an object this massive. Bright infrared and X-ray flares erupt from the region near the event horizon with no clear periodicity and no reliably identified trigger. Multiple observations have caught the emission centroid, the apparent location of the brightest emission, actually orbiting the black hole at speeds close to the speed of light. In 2019, a gas cloud designated S0-2 completed a close approach to Sagittarius A star, skimming past the black hole close enough to test general relativistic effects in real time. The results matched general relativity, but the behavior of the surrounding plasma, the flares, the variable emission structure, these remain poorly understood. The magnetic field geometry near the event horizon, which is crucial for understanding how material accretes and how energy is extracted from the spinning black hole to power relativistic jets, is still being actively revised. The supermassive black hole closest to us is the best studied black hole in the universe. We have its photograph. We have watched stars orbit it for 3 decades. We have measured relativistic effects in real time around it, and it still surprises us. Still produces behaviors our models struggle to fully account for. Still, at the moments of its most extreme activity, does things that our theories can describe only approximately, in frameworks that are valid in isolation, but that break down when forced to work together. This is where physics stands today. 10 anomalies. 10 places where the most powerful theoretical tools humanity has ever built have been pointed at black holes and returned results that conflict with each other, that challenge the foundations they were built on, or that produce predictions so extreme that they have never been confirmed. Scientists have admitted error, revised positions, won Nobel Prizes for demonstrating their own theories were incomplete, and continued working. Not because they are confident they will find the answer, but because black holes are not optional. They are real. They are out there, by the millions, at the centers of galaxies and scattered throughout space. The universe contains them, whether our equations are adequate to describe them or not. And somewhere in the gap between what black holes are and what our physics says they should be, the actual fundamental nature of spacetime, information, quantum mechanics, and gravity is waiting. A theory we do not yet have. A language we have not yet learned. A revision of everything. That will be, when it comes, the most complete reconceptualization of reality since Einstein published his field equations in 1915 and began this entire, extraordinary, humbling, still unfinished conversation. If you want to see more videos like this, click the video on the screen now.